everyone, this week we're going to be learning about electron energy levels, oxidation numbers, and the trends on the periodic table. So to start out, we need to review how many electrons fit into each energy level and discuss again how those electrons in the highest energy level can help us to figure out the charge of the ion. So let's remember that in the first energy level, you will have 2 electrons to fill it up. In the second energy level, 8 electrons will fill it up. And in the third energy level, 8 electrons will fill it up. And you might have learned at one point that 18 electrons fill up the third energy level. We're going to actually get to that next week, but this you can think of it as being full at 8 electrons. Okay, so in this example of chlorine, we're asked how many electrons are in the highest energy level, so the outermost electrons of chlorine. Chlorine, if you look at the periodic table, has an atomic number of 17, and so when it is not an ion, it should have 17 electrons. So if we were to count, in the first energy level, there are 2 electrons. In the second energy level, there are 8 electrons, and in the third energy level, there are 7 electrons. So that means there are 7 electrons in the highest energy level of chlorine. And one term that you need to know is valence electrons. These are the electrons in the outermost energy level. So whenever I say valence electrons, that's what you need to think of, outermost energy level. So this term is one that you should have in your notes for sure. These electrons are responsible for chemical reactions. So they're actually the most important electrons that we could possibly have in the atoms. Alright, so now we wanted to draw a Lewis dot symbol for chlorine. And this is something that, this is new, but when you draw the Lewis dot symbol, you're going to draw the symbol of the element. So for this one, we have Cl, and you include the valence electrons around the symbol of the element. So since it has 7 electrons, we're going to put 7 valence electrons, we're going to put 7 electrons around this chlorine symbol. You're not just going to put them wherever you want. We have 4 general spots where they can go, above, to the right, left, and below the symbol. So 2 electrons will go in each place. But since we only have 7, we're going to only put 1 in one of those pairs. So let me explain what I'm saying. So I'm going to start filling them in. 1 electron goes above, then we move to the next side. We put the second electron, move to the bottom, put the third, to the left side, we put the fourth, keep going around, 5th, 6th, and 7th. So that is all the valence electrons for chlorine. Now, if we want to figure out what its oxidation number is, or the charge of the ion once chlorine forms an ion, because right now it's not an ion, it needs to fill up its outer energy level or empty its outer energy level in order to become an ion. So for chlorine, if it has 7, and it's in the third energy level, the third energy level requires 8 electrons to be full. So that means chlorine can take 1 more electron to become full. Now, when it gains 1 electron, what does that do to the charge? That causes it to have a -1 charge. So if we write the symbol of the ion for chlorine, we would write chlorine with a -1 charge. You can also write it as chlorine 1-. Either way is correct. But most of the time for oxidation numbers, you'll see the number before the sign of the charge, positive or negative. Okay. So I want us to think about which is more likely to gain an electron, oxygen or calcium. So let's use this Bohr model, because this week you guys are going to be building Bohr models again to try to figure out the oxidation numbers of elements. So let's start with oxygen. Oxygen is element number 8 on the periodic table. So that means it would have 8 valence electrons when it is not an ion. So I'll start filling up. I've got 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so like I was saying before when we looked at these kinds of Bohr models, we'll understand why this is the way it is next week once we move to electron configuration. But in energy level 2, there are 1, 2, 3, 4, 5, 6, 7, 8 spots for electrons. And right now, out of those 8 spots, we have 6 occupied. So that means that oxygen would have to gain 2 more electrons to become an ion. So oxygen would then become a -2 charge. Okay, so oxygen is likely to gain electrons. Let's look at calcium and compare it. Let me erase all my oxygen electrons, and I'll go back to red for the electrons that are actually on there when it's not an ion. So sodium has a total of 11 electrons when it is not an ion. So let me start filling those in. Oops, my pen, red. Sodium has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 electrons. So as you see here, we've moved all the way up to the 3rd energy level, and it has 1 electron in the 3rd energy level, and the 2nd energy level and 1st energy level are both completely full. So sodium would have to gain 7 more electrons in order to fill up the 3rd energy level, but it would only have to lose this 1 electron to go down to a full energy level. Energy level 2 is already full. So it's easier for it to just lose that outer energy level electron, and that makes sodium have a charge of +1. And this is because it lost an electron. So therefore, oxygen has an easier time gaining an electron, and that would be the answer to this question. Okay, we're going to arrange these elements on the periodic table based on their oxidation numbers. And this is going to help us to remember or to see that the periodic table is really organized in a way that you can just look at what row, what column an element is in to figure out what its charge would be. So let's look at calcium. Calcium has 2 valence electrons, and it is in energy level 4. Okay, so let me just preface this by telling you that in the upward direction, all of our rows, which we call periods or families, this is also the energy level. It's hard to write vertical like this. Energy level. Okay? So that means that energy level 1 is this first row here. Energy level 1. Energy level 2. Energy level 3, 4, 5, 6, and 7. Okay? So if an atom has something on energy level, has its highest electrons in energy level 4, then it's going to be on the 4th row of the periodic table. So calcium, we know, is going to be somewhere on this 4th row of the periodic table. All right, so since it has 2 valence electrons, we can actually figure out what column it belongs in, because for everything except for except for what we'll later learn is called the D block of the periodic table. The columns represent the valence electrons. All right, so let's verify that that's the case. All right, so if we count across all of our different columns, we've got 1, 2, 3, 4, 5, 6, 7, and 8. Wow, I can't write 8. There we go. So this should help us to see that the reason the periodic table is arranged the way it is because of the electrons and their energy levels. So we know that energy levels fill up at 8 electrons. And so when you start getting to a higher number of electrons and it gets up to 8, then it's going to jump down to the next row of the periodic table, which is the same thing as the next energy level. So the periodic table is a super useful tool, and it can help us with a lot of different questions about the charge and why some elements will react with other elements, and we'll get to that in a minute. So, calcium. We know it's an energy level 4, and it has 2 valence electrons. So that means calcium is located on the 4th row in the 2nd column. So here's calcium. Now, rubidium has 1 valence electron. It's going to be somewhere in the 1st column, and it has an energy level that its 1 valence electron is located in energy level 5. So that means that it's going to be right here on row 5, column 1, RB. And we can actually use this information of where it is located to figure out what its charge will be. So I'm going to actually write in the charges as well. Here, let me make some more space really quickly. Here we go. Now we got some space. So if I wanted to see that the charges can be written in on the periodic table, this is also going to go on the same direction as the columns for the valence electrons. So remember, if something has 1 valence electron, it's easier for it to lose 1 electron than it is for it to gain 7 electrons. So everything in group 1, or the 1st column, will have a +1 charge. The same is true for everything in group 2. It's easier to lose 2 electrons than it is to gain 6. So everything in this row will have a +2 charge. Once we move all the way over to the other side where we have our 3 electrons, it is easier to lose 3 electrons than it is to gain all the way up to 8. So this row will lose its 3 electrons and become +3 charge. Carbon usually is going to be neutral, and this is kind of the cutoff point because it's kind of hard to lose 4 electrons and it's kind of hard to gain 4 electrons. So either way, carbon's usually neutral. If we move up to the next row, which is group 5, these elements would have a hard time losing 5 electrons, but it's a little bit easier for it to gain 3. So these, because they gain 3 electrons, would become a -3 charge, and so on. 6 electrons, it only needs 2 more, so -2. 7 electrons, it needs 1 more, so -1. And then finally, 8 electrons, these are already filled up. Oops. So the last column, these are going to be neutral, and these are our noble gases. They don't like to become ions. So you can actually figure out the oxidation number based on the column. So let's place these last 2 atoms. I already told you where carbon was on accident, but carbon has 4 valence electrons, so we know it's going to be somewhere in this row. We got to figure out which period it's on or which row it's on. And we can figure that out from the energy level. It's on the 2nd energy level, so this would be carbon, because remember the 1st energy level just has these 2 elements, helium and hydrogen, so this is the 2nd energy level.